Welcome, everybody. Thanks for joining us again today. Today, I have here standby with me Oren. He's going to explain all about how to build a database from the scratch. And before we start, please keep in mind if you have any questions, just type the questions on the chat box. And then I was talking to Oren to make a more dynamic session. When the question come, I will ask him, and then hopefully we can have a good conversation. Yeah, Oren, if you want to do a quick intro about yourself, and then I will share the screen and you can take over the
Mhm.
session then.
Okay, so my name is Oren Eini. I've been working in the fields of databases for about 15 to 20 years. For the past, dear God, 12 years or so, I've been writing my own database called
Mhm.
RavenDB. And I find databases fascinating both because of the technical challenge. This is at the heart of what you see as computer science. All of the classical things are right there and super important. And at the same time, databases are seen as this magical beast that does things that you never could imagine.
Mhm.
And it's actually quite the opposite. Most of the things that you see a database do are things that you learn to do in algorithms 101. And
Yeah.
the move from there to actual implementation is a huge step with a lot of details and implementation, but the concept are there and it should be immediately accessible.
Okay. Okay, that's good. Yeah, let me just share your screen, and then I believe we can start. Let me just share in here. Yeah, one sec. Yeah, there you
Okay,
go. Okay, Oren, yeah, you can take over now, and I will be here on the background. If you need anything, let me know. And then, as I said, everybody, if you have any questions, just feel free to type on the chat box, and we will take from there. Okay, Oren, the floor is yours.
thank you. So, as I mentioned, I'm Oren Eini. I'm the founder of a company called Hibernating Rhinos, and the primary product that we build is called RavenDB, which is a NoSQL document database. Now, I'm actually going to show some code. I decided to use the movies and actors and some public data sets that we have here. The idea here is that when we talk about databases, we're typically talking about um, hundreds, thousands of records, which is basically nothing. So I wanted to have something that we can really sink our teeth into it. And you can see here, this is the code that we have that I would walk through for this presentation. And with that said, I want you to think about what is a database. And it's just something that you put data in, and then you get it back, data back. And people just think that, okay, magic. And in some cases, it feels like magic because you throw data into the database and then you query and get it back. And people very rarely stop to think about how it works. And every single senior developer, DBA, have a story about how they went into a poorly performing system and created an index, and the system was so much better. And I remember hearing those stories and understanding that, okay, indexes are important, but don't having a way of actually connecting that to something real for my perspective. I had no idea what actually was going on. So let's talk about what happens for databases behind the scenes. And from outside, what do we have? We have the data model, relational, document, graph, key value, all of those sort of things. How do you query that? Are you using a specific commands like Redis? Do you have JavaScript API like Mongo, a SQL language like relational databases, RavenDB, or Couchbase? How do you do aggregation? How do you work on data beyond just a single record? Inside the database, you have to consider things such as, okay, how do I actually accept a query from the user and run it in the optimal sense? There is something called the lock manager in many databases that manage concurrency between different transactions. Speaking of which, transactions are a huge deal. Do you have them? How do you have them? What is the impact of that? How do you store? What is the actual physical format that you store the data on disk? Another thing that I haven't mentioned, but is also super important, is the notion of what is the interaction model with the database. We're talking about the network level protocol, which sounds really strange. Why do I care about when I'm talking about how a database is built? Why do I care about the network protocol? That's just way up there in the stack. And it turns out that this is actually matter quite a lot, because let's consider two interaction model with a database. In the first interaction model, this is the model that you have for SQL. Insert statement, select, update, and then commit a transaction. The key aspect here is that you have multiple steps across the network with a user think time. So the idea here is that the user may do a select, a second later do an update, a second later do an insert, and then commit. Okay, that sounds like a perfectly reasonable thing to do. But, and I'm ignoring right now the people who have a business transaction that start at 9 a.m. and they commit at 5 p.m. What is the impact of this model of interaction with the database? Well, it means that the database needs to have a really sophisticated system for operating on a data while it is being modified. Because if I did an update on a record and the commit would only arrive in a few seconds, that leads to a lot of complications. I have to do a lock-in. I have to figure out how I'm preserving data that was modified so I can have proper transaction, or much of other stuff like that. The other model is when you accept a transaction, a complete transaction in one shot. So think about it as the difference between receiving a fax with all of the instruction, I want you to move money from account B to account A, versus accepting and doing a phone call, move money from move money out of account A, move that money from to account B, etc. The difference is what is the sort of state that the database need to manage while this is happening. And it turns out that the network protocol and whatever you're using the query per interaction or transaction per interaction has huge impact on how you structure a database. I want to recommend these two books. They are quite excellent. This one, Database Internals, is talking about how you implement a database. And this one talks about how you make use of a database. And I think they are doing a great job of complementing one another, and they cover a lot of really interesting topics. Now I'm going to tell you a secret. Everything about a database starts and ends with sorted data. How you sort the data is a implementation detail. Once the data is sorted, everything else from there is done. So let's talk about what it means for a second. The whole point of a database is to store some data. There is a complication on how you do that with transaction, with ACID, atomic, consistent, isolated, durable. And that can be quite complex. But in the end, all databases end up being some form of sorted structure, and then you can do operations on that. And this is going to be really quite important in the continuation of this talk. Something that I want to point out is the idea that there is a distinction between a storage engine and a database. A storage engine is a component inside the database. This is how you store the data. A database is the interaction model, the data model, the query optimizer, all of those sort of things. And there is a very strong tie between the two, but they can also be quite independent. Here is a good example of several interesting storage engines. Voron is the one that is used by RavenDB and was created by my company. It uses a format called B+Tree and write-ahead log. I will discuss that in a bit, so don't worry if you aren't familiar with those terms. There is LevelDB, which uses something called log structure merge and write-ahead log. RocksDB is an extension of LevelDB. LMDB from CMAS is the core of OpenLDAP. This is a B+Tree and something called a copy on write. SQLite is a full database, but also a storage engine. And same thing, B+Tree and write ahead log, and CouchDB is B+Tree and append only. So the first thing that you should notice is that there tend to be two important distinctions. B+Tree versus LSM, log structure merge. This is related to how you structure the data. Now, the while cow and append only, those are about how you maintain durability of the data. How do you implement transactions? So let's talk about this in a bit more details. Everything ended up being because of this. We have a hard disk. Nowadays, we hopefully have at least SSD, sometimes NVMe, but it's still super, super slow compared to what you have when you're reading or writing from memory. For that matter, we have multiple levels of memory. So when we talk about reading or writing to the disk, we have to understand that this is quite costly. So there's a lot of strategies on how to mitigate that. The simplest possible database is just a sorted array stored on a file. You're done. And we know that doing searches on sorted arrays is quick. In fact, this is not just quick, it's mathematically proven to be the quickest possible way of doing that. Log of n. Great. So what's the problem? The problem here is that every time that you hit the disk, you pay an enormous price. Let's assume that they have 100 gigabyte file that hold sorted records of, I don't know, phone numbers, whatever. And I want to find John Smith. Well, I'm starting to do a search. I'm hitting the middle, disk read. Oh, I'm not, so I heft my search space. Now I have just to do a search on 50 gigabyte. So I do it again in the middle of the remaining 50 gigabyte. Another disk read and another disk read. And it turns out that while thinking in terms of complexity of an algorithm is important, the absurd cost of reading and writing to the disk dominate everything. This is why we tend to structure databases very differently from how we would structure in-memory databases, in-memory data structures. So the first one that I want to talk about is something called log structure merge. And the idea here is that we write sequential files to the disk in some format. The common format is something called SST, sorted string table. And basically, this is just a sorted list of items. The key here is that a sorted string table, the file, have some additional structure that can help us. For example, it may have interior pointers that we can use to jump to the right location. It may have a Bloom filter that we can use to know if a value is there or not. An important aspect of log structure merge is that it is typically written as a single unit. So you write a big file, and after a while you write another big file and more file, and eventually, that's the merge part, you would merge them. The idea here is that you take advantage of a very important property of hard disks, which is sequential writes are very, very fast. The downside of log structure merge is that you may have to modify the data multiple times. This is called write amplification. And we are going to see how this works. Don't worry about that. Write ahead log refers to how to maintain transactions. And that's important. And the idea here is very simple. Writing to disk is very expensive. Writing to disk randomly is super expensive. So what I can do, and a user may just want to write wherever. So how do I manage that? I write my intent. I want to do X, and I write it to a log file, which is of course sequential. So that's much, much faster. And in that way, I can optimize the data access pattern for writes. At some later point in time, I can now take all of the intents that I written to the log and apply them to the data file, thus significantly reducing the amount of work that I have to do. A B+Tree is an important data structure. We will see an example of how it looks very shortly, so we'll skip that for now. Sorted string table is typically how a single file in an LSM looks like. And the downside is that you have to do a merge or compaction. Append only and copy on writes are two alternative ways to ensure durability. With append only, we are writing always to the end of the file. That gives us two important advantages. First, we are writing in a sequential manner, which is great. Second, if we never modify all data, we don't have to worry about corruption. But that means that we have to worry about compaction. I'm always writing to the end of the file. Let's say that I have a database that will tell a single value, which is a number, and I'm always incrementing this number. So every single increment, I'm going to write it to the end of the file. What about all of this, which is now still data? I have to run a compaction to recover the disk space. Copy on write, which is something that is used by LMDB, is another approach on that. It is saying, okay, I'm going to overwrite the value, I'm going to, whenever I want to modify, I'm not going to overwrite in place. I'm going to copy that to a new location and do all of the modifications there. And that and then I'm going to mark the old location as available for reuse. And that makes things a lot easier for us because I don't have to worry about how do I maintain the old state and new state at the same time. Sorted data, as I mentioned, is super important, especially because you have multiple access that you have to look up the data. For example, in the phone record example, I have do search by do search by name or by location or by if I'm talking about a commercial book, by industry. Give me all of the electricians that are near me or something like that. So think about how you would do something like that. How do you search all electricians near me? And it sounds really complex, but it ends up actually being just playing around with various forms of sorted data. I'm going to give you an example, and all of the work that we're going to do today would be on top of LevelDB. This is a storage engine that came from Google. I've actually written an 18-part blog post series on that thing, so you can go and read that if you're really, really that interested in the topic. And let's look at this. This is how LevelDB works. You start by writing entries. The LevelDB is a key value structure. So you write an entry and it's get written to one of those files. And now here are the rules. Each one of these files is sorted internally. Now, if I want to search a value, the first thing that I'm going to do, I'm going to go and search all of those. But eventually, let's say that each one of those is 1 megabyte in size. Eventually, I'm going to have way too many files. So what I'm going to do, I'm going to run a merge step, and I'm going to scan all of those items and merge them into the next level. And the key difference between level 0 and level 1 is that for level 1, we are guaranteed that each file contains its own range of the key space. And what does it mean? In here, in level 0, I have to scan all of those files. In level 1, I know that if I'm searching for John Doe, it can only be here because this is the sorted nature of this. And then it goes down deeper, all the way, I think, to 7 or 10 levels, something like that. And the data model that you have is actually quite simple. You have the notion of sorted dictionary of key and value. And the key is some binary or string, the value is some binary value that you want, and that's it. Now, importantly, what we have is very simple interface. You don't get a lot of operations. You have get me an item by key, delete the key. There is also a set, obviously. And most importantly, you have notion of iterate. And iterate means one thing, iterate in order from a particular position. Now remember, this is actually sorted. And I keep saying sorted and because it's that important. So let's talk about the movies. Let's see how we can write some code and see some movies and have some fun. So this is what I did. I went to the Internet Movie Database and I got the names and the titles of a whole bunch of movies. And you can see that this is the structure of the data that I have. If you recall, I told you do a wget on a bunch of things, and this is what we got. So what you can see here is the build your own database repository. And those two are the data file that I have. And let's see if I can open in Explorer. So you can see this is this guy and this is this guy. So compress and 200 megabyte, 150 megabyte, reasonably sized. Now, the first thing that I want to do, I want to load the data into my database. So I have something that basically says, open the file, read it, translate that into some format, whatever, something for this, and now I'm deleting. This is the database directory. You can see it here. We will inspect that in more detail later. Now I'm dropping that, creating a new database directory, and I'm using here something called Plivel, which is an interface to LevelDB in Python. I'm using Python because it's very simple and allow me to focus on the major concepts. And what I'm going to do now, I'm going to load 500,000 records. This is the limit that I have here. I'm reading the titles. And then all I'm doing, I'm reading the title, I'm reading the names, and I'm calling put on the entire thing. That's it. Now, this takes about 17 to 20 seconds on my end. If I wanted to load the entire data set, it would take about 5 minutes on this case. This is not doing that in the most efficient way possible. This is doing that in a quite bad manner, but I don't actually care. Now, I want you to show, now I want you to see what the data looks like inside. And let's see if I can. This is the data. NM here is Fred Astaire, Lauren Bacall, not really that interesting. By the way, apparently I have to, and this is more or less how this works. So I'm basically saying, okay, open the file, open the database, start scanning that. Notice that I have a prefix, that would be very important later. And now we can see it in more details. Really not that interesting. And the question here is, what do we do? So here's a set of steps that we did. So far, so good. This is data. I can now go and read that. I can do stuff to that. This is a database. It's a really silly database, I would admit. This is a database. You can see here, those are the keys. And this is the value. And the value just happened to be some JSON. Why is it JSON? Because I asked it to be JSON. I could have used a pickle, I could have used XML, whatever. LevelDB doesn't care. Our database that sits on top of the storage engine actually bring meaning into this. So this is what we did. And now we want to start actually applying certain operations. So we saw the code to dump all the data. Now let's say that I want to look at Fred Astaire. This is what I'm doing. I'm calling get on the key that I get. Let's look into that. Here is Fred Astaire. Here is the call that I need to do. Notice that I have all of those as well. What happens if I start looking at those? What are those in the first place? Notice that I'm saying known for titles. So let's see what happened when I'm looking at this guy. Here is on the beach. So what I'm actually doing here is doing this. Go and get Fred Astaire by its key. Search for its known titles. For each one of them, get the value of the relevant movie and then print it out. Which means that I get this really nice detail about Fred Astaire. Now think about what this actually means. Because this is what we did. Look at the query. We have actors and we have titles, and we did a join between them. And if I was using SQL, I would have actors to titles table. But I don't actually have an actors to titles table. Why is that? Because my data model allows me to store an array here. So I can store all of that in a single location. If I was using a plain key value store, that would be quite different. But this is what we actually did. Now, let's go for a second. Look at this directory. And what do we have here? Here we have some really interesting things. Those are files. You can see those are relatively small files. And then we have a few megabytes. And in the end, we have 2 megabyte files. Those are the different levels that we have for LevelDB. And this points to where we're at. This is the write-ahead log for LevelDB. And when we have data, if we want to do something like this, search for Fred Astaire, how does it work? We call get. What happens then? Well, we are scanning all of those files because those are the level 0 files. And we're saying, hey, do you have, for each one of those 6 files, do you have any, do you have 5 files, do you have any Fred Astaire in you? And they're sorted, so this is all log n of each one of those. Okay, it's not there. So now I know that I have to go to this file because this is the only file in the next level that can contain Fred Astaire. And if it's not here, then I have to go to this one, which is again the file that owns the range of Fred Astaire in the next level, and so on and so forth. Practically speaking, can assume that this is an O log n operation. By the way, this is also O log n operation. This is an n operation. So the total cost of the details is something like O log n to get the values. And this is number of titles, like this. And notice that we now have a really good understanding about how this thing actually came to be. Now, this is quite trivial. Honestly, this is really, really easy. But look at the query and compare the complexity of the JSON to what we're actually doing behind the scenes. Now, to be fair, this is easy. The complex part is to be able to take this and then translate that to what's actually happening. But the whole idea in what we are doing and the reason for this talk is so you understand how that works. Now, let's make things a little bit more interesting. Right now, everything sits in the same place. If I'm going to dump, I can see here all of my actors, but also here all of my titles. They're in the same place. And that complicates things. What happens if I have an actor with the same name of a title? So in SQL, we are used to having tables, which bring more structure, which make things more easier. With level DB, we have the notion of a prefix. And you can see it here. Where is it? Same thing so far, and here we go. Here's a prefix. Here's a prefix. So now, instead of doing a DB put, like we're doing here, we're going to say title put. And instead of doing a DB put here, we can do actors put here. And in practical terms, it does the exact same thing, right? I mean, okay, so now we have an actors and something like that. Let's see how this works. So what I'm going to do, I'm going to run the, and again, on 500,000 records. This takes about 20 seconds. And then we'll be able to see what the structure of the data looks like. Now, in practical terms, we haven't really done much. Nothing really that interesting. Okay, add a prefix. Okay, why do we care? Aside from being more organized. Let's see. Okay, so actor slash nm blah, 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 blah. Wow, amazing. Well, let's look at this. Previously, I said, let's go from the user to the, let's go from the user to all of the titles they are known for. So this is what we did here. And sorry, that's not load. This is and you don't like me. Why don't you like me? Sorry, I accidentally ran the one load again and that deleted the data. I have to do that again. So anyway, so what we're going to do, we're going to run the same details again. This time we're going to pass it the actors nm blah blah blah, and then we're going to see further stuff. And that's trivial to do, right? because we can walk from the actors to all of their titles. And now I don't actually have titles for this because I change how this works, but you can see how it works. I have to add actors here. And what I want to do the other way around. So let's see how it works. Now, and great. So this is the tower in Inferno. Here is Fred Astaire and a whole bunch of other people. How is it implemented? Here are the relevant prefixes. I'm saying give me the title for this movie. Perfect. Print the actual name of that. Let's make this. Now go over actors and check if I'm there. And this works. We're happy. Are we happy? Well, almost. Look at this. This is 1.7 seconds to answer this query. I have to scan the entire operation. ON. As the size of my data grows, so will this. That's too expensive. Can we do better? Now I'm getting to something really interesting. Now I have something called index actors by title. What is that? Let's see here. Here, when I'm reading the names of actors, I'm checking if they are known for a title. And for each one of them, I'm doing this really weird, strange thing. So title concatenated with the key. I don't understand that. Let's look deep into what is involved. And now this shows me something really, really strange. Look at this. So I'm going to ignore this piece because this is just a prefix that I have here. This is what is important. Title, pipe, key. Title is the title of a movie I'm known for, and the key is the key of the actor. Okay, how does it help me? Well, remember, this is sorted. Now I'm scanning for this guy. Not, let me test something. What happened if I did this? Here all of the items in the database that start with this prefix. And here is Fred Astaire, NM001. I'm going to assume that 740 is Irving Allen. Let's see how that works in code. Here is actors by title. Here is, what's that? That's interesting. You have a prefix of title ID. So now I'm saying, give me actors by their title. Let's see. So this is the title ID. And now we have this. So this is the title of the movie. And now I'm saying, give me all of the results that start with this. Now, to be fair, this isn't actually that good. We should use this instead to make sure that if I have titles that aren't in the same length, so I have this separator between them. Now let's see what are the costs that are involved here. This is the scan. Cost me 1.6, 1.7. This is the query. Look at this number. Same result. Fred and Irwin and all of that. And what I did, I went to the position in the index for this. Then I just extracted those values. Notice, by the way, that I have a key for each one of those, and then a value. And the reason I have to have this format is so I can have multiple keys for this. So this is the for this title, for this title, for this actor. Practically speaking, I can probably just put none here and save the space, but it makes it easier to just get this and not try to figure out what is the actual key and extract and something like that. It just works. It just works in a very simple fashion. That's it. Prefix search on the index. All again. Instead of 1.7 seconds, I have 40 milliseconds. By the way, all of those types include initialization costs. Spinning up the Python interpreter, opening the database file, opening all of the files, those sort of things. So the actual numbers that you're seeing is actually going to be far more impressive. Now, this is a more complex one. Find me all of the actors that worked with a particular actor. What? Try to think for a second about the kind of query, the SQL query that you would write for something like that. And consider the internal data structure that we have. Here's how we can write this. First of all, let's look at Fred Astaire. Here, he is a big actor. So all of the people who work with Fred Astaire. And here's how we compute that. First of all, we get the actor, we get Fred. Now we are getting all of the titles that he participated in, or known for. And now for each one of those, we compute the people who worked there, which is basically running this query, which you just did. And now we're just putting that in a set, skipping my one, and that's it. Skipping Fred here. And that's about it. Now look at this code and try to imagine what the query is going to be like and understand that this is what actually happened behind the scenes. We get this from the actors. We scan all of the actors who played in the same movies that Fred Astaire did. And then we get those actors and print their name. Now we're done. As easy as that. Here is a more complex topic. I want to do a search. So let's see how I do that. Sorry. I want to search for mangoes. That's interesting. Mango tree, tamango, do it with pamango, whatever. I don't even know what that is. If the mango tree could speak, wonderful. Total cost, 1.8 seconds. That's kind of expensive to me. Can I do better? And look at what we're doing here. I'm defining a full text search on title. And now I'm doing something really, really interesting. Look at this guy. Give me the primary title, split it into words, and do some cleanup and write it here. So let's do this. This is going to run. Now, all of this code that you're seeing here, this is the equivalent of doing a create index. We're adding a new index to an existing database. So you can see that we are scanning through all of the titles and generating some data. Now, let's look at what we actually got. And let me just slightly more interesting. Mango. Okay. So what happened here? We are saying, okay, let's take the title of the movie and split it into words. Clean it up a bit, so remove commas and periods and stuff like that. And then create an entry of Mango, pipe, and then the key. What is the key? The key is the key, the movie ID, the title ID. And that's it. Now, when we want to run a query, we can do it like this, which basically is very similar to what we're seeing here. So let's see that. We're doing a search for Mango. This is 1.8 seconds. Query, well, that's far, far faster, 32 milliseconds. Now, there is something here that is really interesting to see. Look at the number of results. Let me just do that. And have it on scan as well. So let's see this now. Save and save. So we get 13 results for query. For scan, far slow, we get 22. Why do we have this difference? And the reason is this. You see that we have Pamango, but here we don't have Pamango. Why is that? When we do a scan, we check if this term is inside the lowercase title. And Mango, the string, is indeed inside Pamango. But here we're not doing that. Here we are responding to the data that we have in the full text search index. And here we just split it according to whatever rule we have. In this case, basically split it on space. The difference in functionality is that now mangoes, but I won't have mangoes here because it wasn't split this way. For full text search to work properly, I have to do, this is called tokenization. I have to take the title and break it in smarter ways. Oh, I know that ES is actually the plural form. Let's remove that. Apostrophe S is the possessive. Let's remove that. There is a whole world around how you do the tokenization process in order to get the right terms. For example, you might want to, instead of tokenizing the words, just use something called n-gram. So you're going to say, oh, I'm going to generate from each one of those words a series of permutation, and then I'm going to be searching on that. Sometimes you have to find the stem of the word, the root of a word, in order to handle that. But I'm not going to touch a lot more on that.
Yeah, Oren, sorry to interrupt you. Yeah,
Absolutely.
I think you are explaining too well so far. We don't have any questions. I have a question myself. I'm not
Mhm,
a DBA. I'm not a database guy. I'm
mhm.
just wondering. Let's say if that database, yeah. By the way, is a great, let's say, a way to make it more. Let's say to make it faster. My question is, if the database is on Azure, or any other cloud,
Mhm.
can you still get this huge performance when you do the tweak on the query?
Every single time, yes.
Oh,
Because
nice.
in
Okay.
because in the end, this is what happens.
Mhm.
Let's talk for a second about um, this thing, because this is easy.
Mm.
We have
Again, Oren,
yeah,
before
mhm,
I forget,
mhm,
let's
yeah.
say because the query is so much faster, if you are dealing with a huge database, I believe
Mhm.
at the end you will get a good advantage on the cost as well because things are faster. Or do you know if it
In
affects the cost
yes,
as well?
yes, absolutely. So let's talk.
Brilliant.
Let's talk about this thing.
Okay.
What are we doing here? And we can see the cost here. Let's do a search on Scat. What's your problem? It's supposed to be. I messed something up. Uh, oh yeah, because I need to be talking about title. Sorry. Uh, and that was 740, I think. Fred Astaire is. One second. I will use my cheat sheet and better than trying to remember that. Okay, so here we have this guy. Okay, so you can see that this actually costs us this amount, right? 1.8, 1.6 seconds. Uh, so now I'm running IOTop, and this is not enough to see that, but what you should be able to see in some cases is that we are actually using, we are doing more reads. Let me do this. This is the amount of work that you're doing. And you can see here that there's quite a lot that is going on. If we go and do the same but using a query, the amount of work that you have to do is far, far less. And the amount of work is translated into everything that's going on. The amount of CPU time that you're spending, the amount of IO that you're generating, all of that are things that you're actually paying for. Now, think about what we're doing here. What we're doing here is basically this query, or similar query, basically. And
Yeah, now with the last example, even for a
mhm,
guy, not a DBA, not a
mhm,
database guy, yeah, now I could really see the difference. And
yeah,
then,
and
yeah, that will translate
especially in
on
the
the
cloud,
entire cost.
this
Yeah,
is what you're paying for.
that's right. Yeah. Hmm.
If you don't have an index, I have no option from database perspective than doing this. This is ON.
Yeah,
Now,
makes
the
sense.
more data you have, the more I have to read, evaluate it, and discard or accept. If I'm able to do this, then hey, this is an O log N.
Hmm.
Now I'm in a much, much better position.
Yeah. Anyway, all clear for me. Yeah. Okay. Thanks very much.
Okay. So when you think about it, you have to think about the design structure of your data, because if you have the sorted data and the key space, then that gives you all of this flexibility, the indexes, the table, so to speak. The fact that this is sorted means that I'm able to execute queries, fast queries. And you could see that just for being able to do uh, uh, prefix search and things like that on the data, I was able to issue what is effectively a join quite efficiently. And let's say that I want to do something such as a spatial search. How do I do something like spatial search? Well, let me show you how you do that. Uh, uh, it should be here. Okay, so let's say that, and do I have some way of doing that? Okay, one second. Let me see if I can show you a better example. Not really helpful. I want to see that on a map in a nice way. And I can do that. Okay, hopefully this will be it. So basically, I have a way of looking into a map and seeing. See this value? This is precision that I need to cover, and I don't even know where this is at. So this is somewhere in France, and you see QBS. So this is, if I want to find something in Brest, now I can narrow things down. But this is it. So what I want to do, if I want to say, hey, I want to find somewhere within a particular range of Saint-Renan. So okay, give me everything that has this prefix, and then just check whatever this is far enough or not. So just being able to do unsorted data, I now jumped to GeoHash, and now I have the ability to do spatial queries. All of which is now I'm able to do in O log N. So as the size of my data grow, my performance remain more or less constant. Indexes are actually that simple and obvious. Even if you don't want to build an actual database, then understanding how the internal work matters, because then you can do what you're asking the database to actually do. And now you can actually utilize that to make your software better. Now, here is some additional information. Now, this is a B+Tree. A B+Tree is a page. This is a 4 kilobyte, 8 kilobyte in the data. And this is how the data is internally structured. So now let's say that I want to find entry 102. I read the root page. This is one time going to the disk, and I can see that 102 is not here because this is everything that is less than 102. 102 is here because this is 102 to 209. So now I have to read this page. And now this is a second read. I get this 8 kilobyte, and now I have 102, and I had 2 reads from the disk to get the data. There's a lot of details here that matter. For example, you may have multiple trees instead of just one. In 11db, for example, everything is just one single key space, and we may use prefixes to manage that. Other systems have multiple key spaces. For example, a table in a relational database would typically be its own B-tree. The insert order matters a lot. Why is that? Because if the data is sorted, then I effectively think about how you would create a sorted array. If you add the data in a sorted fashion, it's just always append to the end. In the same manner, if you work with sorted string tables, with B-trees, adding the data in a sorted manner is almost always the best scenario. There's all sorts of details that you need to handle. They don't matter that much from a conceptual basis, but they're fascinating if you want to understand more about what's going on behind the scenes. The most important details that you have to remember is that this is slow, so slow. And everything about managing databases is about accepting that fact and moving on with that. And with that, I'm almost on time. This is done for questions.
Yeah, great job. Thanks for that. Yeah, we didn't get any questions from the chat box. I think people kind of managed to understand all the steps you provide, and yeah, that was great. Even for a guy like me, let's say now I can say I have a better understanding about all the databases and stuff. Yeah, that's great. Yeah,
Okay, I'm very happy to hear that.
yeah. Um, okay, yeah, if you are kind of done with your presentation, one more time, thanks very much, Oren,
Mhm.
for joining us here and spending, let's say, the last hour with kind of deep dive into the database. And thanks very
Mhm.
much, everybody from home, to be connected with us for the last hours. And please
Okay,
keep your eye on our website for the upcoming sessions as well.
bye
Okay,
bye.
Oren, thanks very much, Oren. All the best, and thanks very much again. Yeah. Okay, see you next time, everybody. Thank you.